Hi everyone, I'm going to record myself with the worksheet 10 solution and try out this way of posting solution. Let me know if it's more helpful than just directly posting the solutions. Okay, the first one is you're trying to show that the circumference of a circle is 2 pi r, which is a formula that you know. We're going to use calculus for it. Because circles are transformatively equivalent, it means we can just look at a circle centered at origin, whose equation is x squared plus y squared equals r squared. From here we get 2x plus 2y dy over dx equals 0 because r squared is constant. So negative 2x is 2y dy over dx, or we get dy over dx is negative x over y. Now arc length is going to be, let's say I go from negative r to r for x value, 2 pi, just square root of 1 over 1 plus dy over dx squared dx. Now because we have a symmetric integral here, the total arc length is going to be 2 times half circle, which further becomes 4 times just the first quadrant dx, and then we can utilize some of the information given to us. For example, when you combine these fractions, you get that, but we already know x squared plus y squared is, it's just r, right? So we get 4, 0 to r, that's r over y. Now what is y? It's r squared minus x squared dx. And this is a typical trig integral, so probably x equals sine theta will work, which gives me dx is r cosine theta d theta. Limits when x is 0, theta is 0. When x is r, sine theta is 1, which means theta is pi over 2, which should intuitively make sense because we are in quadrant 1, so that's 0 to pi over 2. What else? R dx is r cosine theta d theta. The whole point of the substitution is that the denominator is r square minus r square sine square, which is r square 1 minus sine square, which is r cosine theta, right? So that cancels out. So we're left with 4 times r and pi over 2, which is just 2 pi r. And that's the formula that we already know for circumference of a circle. We can derive that using calculus. Second one is concerning length of a catenary, which is usually the shape taken by electric supply lines or anything suspended between two heights. It kind of looks like a parabola, but it is not. The equation is c plus a cos h over x over a, Now I don't want to work with the cos and the sine expression, sine h, so I'm going to change this into the exponential form. You don't have to, I am basically changing it into exponential because I don't remember the derivatives integrals of cosine h and sine h, but the exponential functions are easier. So I take the derivative dy over dx, constant becomes a 0, a over 2, derivative of e is ex to the a, chain rule 1 over a, e negative x to the a, 1 over a. Factor out a 1 over a, and I have ex over a minus e negative x over a. So dy over dx is this term, which is basically sine h of x over a, right? which if you directly take the derivative and you remember what it is, it should give you the same answer. But because I don't, I just took the long route. So basically, you don't have to remember those derivatives if because they can be written in exponential form. So the length is going to be negative p to p 1 plus sine h squared of x over a dx. Now symmetry argument works again, so 0 to b, and that's going to be square root of 1 plus sine h square x over a dx. Okay, now this is an identity, 1 plus sine h squared of something equals cosine x square of something, right? So this just becomes 2 integral 0 to p cosine h x over a dx, which again I don't remember, so I'm going to change this to exponential over 2. The 2's conveniently cancel out. Integration is x over a divided by 1 over a, so that becomes multiplied by a, and same thing here, going from 0 to b. So what I have here, when I plug in b, well, let's check the 0. When I plug in 0, it's a minus a0, so we don't have to worry about it. When I plug in b, it's e to the b over a times a minus e to the negative b over a times a, which is a times e to the b over a minus e to the negative b over a, which if you want to write in the hyperbolic terms could be written as 2a e to the ba minus e to the negative ba over 2, or 2a, the negative means it's a sine h of b over a, which if you directly apply, I guess the integration of cosine h is sine h, right? And you get a, so it kind of works out. That's number 2. Number 3 is the fat circle. So we have x to the n plus y to the n equals 1. This question is a little challenging. Hopefully you went to Desmos and looked at what it looks like for different values of n, particularly even values. So what you should have seen for square, we know is a circle, and then it sort of starts expanding in shape and form, and as you increase, it's going to resemble a square, and that's why it's called a fat circle. So let's try to set up the arc length for when n equals 2k. So I have x to the 2k plus y to the 2k equals 1. So y to the 2k is 1 minus x to the 2k. I take the derivative, I take the root, so 1 over 2k. Now I take the derivative, keeping in mind chain rule, so the exponent comes down, x to the 2k, 1 over 2k minus 1 times derivative of what's inside. Derivative of 1 is 0, so this is negative 2k x to the 2k minus 1. These cancel out, so I have a negative 1 minus x to the 2k, 1 over 2k minus 1 times x to the 2k minus 1. That is my dy over dx. Now what that means is that my expression for arc length, let's call it L2k, is going to be integral of 1 plus dy over dx squared. So 1 minus x to the 2k, 1 over 2k minus 1, all of this squared dx Let's say x goes from 0 to 1, so we are restricting ourselves to quadrant 1. Okay, so that's all the problem asks you to do, not to solve it because it's not possible to solve in the form it is. But the next question was sort of combine your observation from Desmos as to the fact that it becomes a square to try and guess what this limit should be. Now this part is a little tricky. Now we observe that as k goes to infinity, it sort of resembles a square, and it has these points, sorry, 1 1, negative 1 1, negative 1 negative 1, and 1 negative 1. Right, so it's a square of side 2, which means intuitively this, whatever we captured using calculus, should give us a perimeter of the square, which is 2 plus 2 plus 2 plus 2, which is 8. So let's look at this limit. Right, let's see what happens to okay. Now as k goes to infinity, in quadrant 1 we have this shape right here, which means x and y, they are approaching the value of 1, right? So as k goes to infinity, this term, it sort of disappears. Okay. Now another thing to note here is, although we are in quadrant 1, we are sort of there are 2 branches that are being counted here, right? Which means that this, whatever length we get when we apply the limit, is only going to be one of the vertical branches. So it only gives us this length. In which case this would be, this would just become 0, giving us this length to be 1 for one of these branches. So to cover for both branch in quad 1, I need a 2 times, and then I have 4 of these, giving me 2 times 4, which is 8. Problem 4 is an ellipse that is being rotated to form what is called an ellipsoid, and in here you can again verify by plugging in values for a sphere. We're finding the surface area. So in general the surface area would be 2 pi y, gives me the length, and then this height is the arc length, so it's 1 plus dy over dx squared dx. You can quickly find the x coordinates, or sorry, the x intercept, which is going to be a0, negative a0 and a0. So our integral goes from negative a to a, or 2 times 0 to a, owing to symmetry. Okay, so now let's do the calculation part. If you take the derivative, this is 2x over a squared plus 2y over b squared dy over dx equals 0. So that dy over dx is negative b squared x over a squared y. So 2 pi y under root 1 plus negative bx over a squared y squared. Let's not throw in the integral yet. Let's see if we can simplify this. That becomes a b4x squared plus a4y squared over a squared y. So that's good. One of the y terms cancel out. This is 2 pi over a squared. Now we gotta change everything in terms of x. Now from the equation, y squared is b squared times 1 minus x squared over a squared, which means a to the 4y squared is a to the 4b squared minus a to the 4b squared x squared over a squared, which simplifies a little bit. So this is b to the 4x squared plus a to the 4b squared minus a squared b squared x squared. Okay, simplifying this further, this is a to the 4b squared minus x squared, a squared b squared minus b to the 4. Now let's try and simplify some stuff. I'm going to factor out an ab. When I do that, that's actually a squared b squared from inside, so this ends up a squared minus x squared I factored out an a squared b squared. So that would be, oh wait, it's not, okay, let's factor out a b first, so don't make a mistake. Leaves me with a to the 4 minus x squared, a squared minus b squared. Alright, now let's factor out an a squared. So that's going to leave me with a squared minus x squared, a squared minus b squared over a squared. Alright, so now I set up my integral. I have 4 pi b over a going from 0 to a, square root of a square minus x square with the coefficient of a square minus b square over a square dx. Now I don't want to work with this messy term, so what I'll do is I'm going to let lambda equal to square root of a square minus b square over a. So this integral now becomes 4 pi b over a, 0 to a square minus x square lambda square dx. Now this is a classic trig integral, so I'm going to let x lambda be some a sine theta. When x is 0, theta is 0. When x is a, theta is arc sine lambda. In addition, dx is a cosine theta d theta over lambda. And of course, the whole point behind the trig substitution was to change this guy into a cosine lambda theta. But then I also get this another a cosine theta over lambda from changing the dx. So I have 4 pi a squared b over a 0 to arc sine lambda cosine squared theta. Let's get the lambda outside as well. Okay, so let me just rewrite this neatly. 4 pi a b over lambda 0 to arc sine lambda cosine squared theta d theta. Okay. Now, and I'm going to use this identity. Cosine 2 theta is 2 cosine squared theta minus 1. So that cosine squared theta is cosine 2 theta plus 1 over 2. So 4 pi ab over lambda integral 0 to arc sine lambda 1/2 plus cosine 2 theta over 2 t theta. Alright, that's 4 pi ab over lambda. That's just arc sine lambda over 2 plus 1/2 sine 2 theta over 2 arc sine lambda. Sine 2 theta is 2 sine theta cosine theta. So this is arc sine lambda over 2 plus 2 sine theta cosine theta over 4, 0 to arc sine lambda. This cancels out. Now when it's 0, it's just going to be 0. However, we can use a triangle here, right? Because by definition of theta, sine theta is lambda, so cosine theta is adjacent over hypotenuse. Okay, so what we have here, oops, let's pull out this, get this 2, that's the lambda, sorry. So 4 pi AP over 2 lambda arc sine lambda plus sine theta is lambda 1 over 2. Okay, yeah, I'm doing that right. So that should be my final expression. Now to verify, we say that when A equals B equals R, then it becomes a sphere. So we're sort of talking in the limit. Now in this limit, as this happens, lambda is going to approach 0, right? Recall, because lambda was square root A square minus B square over A. So we are interested in finding what happens in the limit that lambda goes to 0 of this expression. And so you have 2 pi AB, then you have arc sine lambda over lambda plus 1 minus lambda squared over 2. I think I have an extra factor here. Alright. Let's see. 1/2 2 sine theta should give me a 2. Right, when I pull this 2 out here, I shouldn't have this 2. Okay. Now what's the limit of arc sine lambda over lambda as lambda goes to 0? That limit is 1. And this is 1. So you get 4 pi AB. But in addition, A equals B equals R. So for sphere, that's going to be 4 pi R squared, which is the formula for the surface area of a sphere. Alright, the last one is Gabriel's horn. R is x, y, x greater than or equal to 1. So this is a shape which has a finite volume. So you can keep a finite amount of paint, but you can never paint it because its area comes out to be infinite. So this is what it looks like. Goes on to infinity. You rotate it, and we're finding, so 2 pi y, which is 2 pi 1 over x, 1 plus 1 over x to the 4, 1 to infinity, right? Well, because dy over dx is negative 1 over x squared. Okay, let's go ahead and set 1 plus x to the negative 4 as u, so that when x is 1, u is two, and when x is infinity, u is 1. Okay, so 2 to 1, and the derivative over here is negative 4 x to the negative third dx equals du. So I have 2 pi over x root u du over negative 4 times x cubed, which cancels out. So I have negative pi over 2, 2 to 1, x squared du. Now that's no good because we want everything in terms of u. So let's see, x to the negative 4 is u minus 1. So x squared, or x to the negative 2 will be root u minus 1. So x squared will be 1 over root u minus 1. Oh, sorry, I forgot a root u. Now, I don't want this negative in front, it doesn't look nice, so what I'll do is I'm going to switch these, and the negative times negative becomes a positive. So I have root u over root u minus 1 du. Okay, now this is a case of an integral which has a problem point here, right? Because when u equals 1, this thing blows up. As it goes to infinity. So let's keep that in mind. Keeping that in mind, let's do a limiting thing here. T goes to 1, t to 2, root u du over root u minus 1. Okay. Let's do another substitution. Let lambda equal root u minus 1. D lambda is 1 over du. So du over whatever this stuff is, limit t going to 1. Let's also look at the limits, right? So when u is t, this is root t minus 1, and when u is 2, this is 1. Alright, so we have a root u. Right, you have a root u and you have a 2d lambda. Okay, so lambda square is u minus 1, so u is 1 plus lambda square, pi over 2, I'll get this 2 out, limit t goes to 1, root t minus 1 to 1, 1 plus lambda square t lambda. Okay, we have to, now that's a trig integral which can be solved using tangent. Right, so let's lambda equals tan theta, d lambda is secant squared theta d theta. I'm just gonna find an indefinite integral. So this is going to be secant theta, secant cube d theta, u equals I feel like I'm going around in circles here. D theta secant theta, so 1 plus tan squared theta d theta, u equals tan theta. Oh wait, secant squared theta and secant theta d theta. Oh, that's gonna send me back there. Okay, good. So this under the limit should give me infinity. I cannot remember what. He's gonna try and get the integral table up here. Why is it so small? What is the square root of 1 plus lambda squared? Nope, that's not helpful. Why is this not on the table? Okay, this video is getting too long. I'm going to post another video with the last part of this problem.